All right. Now this one's kind of fun. This is Journey to the Center of memcopy. So here I'm hunting for a repeat move instruction. So I want to find repeat move because it's kind of interesting. And a good place to find repeat move is memcopy because repeat move is functionally a memcopy in one thing. I said rep stos is kind of like a memset. Rep move s is functionally like a memcopy. And it's used in certain situations, and we'll get into it. So anyways, here's what we got in terms of C code. All right, so I'm type defing a struct just so that I can have the name of the struct to be called mystruct_t. So I define two mystruct_t's over here. And a given struct is a single integer called var1, and then an array of 4 bytes called var2. So when I define my struct A and B, what I should expect is I'm going to have one struct on the in my local variables, and then the second struct in my local variables. And I think it's even A is at the top and B is at the bottom, where top and bottom are like I have over there. Then I'm going to just, set var1 equal to ff. That's just because I'm going to copy var1 onto var-b, or sorry, I'm going to copy A onto B, and I just want to prove that I copied it onto that. So, I set a single value just so that I can see if I did the copy, then when I'm done with the copy, b.var1 should be equal to ff, whatever it is, either 0, 0, 0, 0, ff, I think. So I'm going to do a copy where I give the address of A, the address of B. So B is the target, A is the source, and the size is the size of my struct. And then I return a sub base. Cool. All right. So I have this all written out, but I'm going to try to figure it out on the fly. All right. So I'm going to go into example 9. Set that as the starter project. And this one, you can follow along as well if you'd like. Or you can just watch me. So, here we go. Memory window. All right. So, the whole point of this one is there's no new instructions in the assembly for what we're seeing right now. And I'm hunting for a specific instruction. And if I step into memcopy, that's where I expect to see the specific instruction. So, standard function stack frame setup. Allocation of space for our local variables. This is hex 10, so it's 16 bytes because we have 2 structs, each of which is 8 bytes, right? It's a 4-byte integer and a 4-byte array. So 2 times 8, 16. All right, and then the first thing we see right here, right away, is move ff, and this is, taking the zeros and extending it, so it's still a 32-bit value, but it's all 0, 0, 0, 0, 0, ff. Move that into EBP minus 8, right? So now we know EBP minus 8 is my struct, it's A.var1. So now I'm going to reset our picture here to make it be the picture for this one. DP, save DBP. All right, so we did our first couple of instructions. We did our push EBP right there. We did our move ESP to EBP, or yeah, move ESP to EBP, so EBP points there now. And then we did subtract hex 10 from ESP, so it goes down by hex 10. This right here is hex 10. That's hex 10, and therefore that right there is hex 8, and therefore right there is hex 4, right? So the very first thing I see is EBP minus 8 is set to 0, 0, 0, 0 FF. Right? Well, this is EBP minus 4. Right there, and that's EBP minus 8. All right, so we know now that this is a dot var1, right? I set this, so this is a dot var1 equals 0x123456f. Right? So our C code says set a dot var1 0000ff. Our assembly code says, well, I'm setting something at EBP minus 8 to 0000ff. All right, so I can now infer the rest of everything here, right? This is a dot var1. This must be a dot var2, which is, that 4-byte array, right? Character array. This must be b dot var1. And this must be b dot var2. Right? If these structures have the same definition, and if I think that I've allocated 2 of these structures, then that's probably what I have. All right, so now I'm going to do a mem copy, right? And in order to do the mem copy, right, I'm going to push parameters from right to left onto the stack. So first parameter I need to push, size of my struct. Okay, well, size of my struct is 8. It's just 8. Size of is not like a function. Just as recall, it's behind the scenes. It's like a macro, which is, it's a macro because it's a preprocessor thing that says wherever you see size of in the preprocessing, figure out what that size of that struct or that data variable would be and just like stick in the constant, right? So it did. It stuck in the constant. Constant is 8. That's the size of my struct. So already pushed that onto the stack. All right, so got size of my struct right there equals 8. Pushed that onto the stack. ESP goes down. I'm not going to update ESP each time here until we get done pushing everything onto the stack. All right, then I do LEA of EBP minus 8, and I put that into EAX, right? So what is LEA? That says take whatever this address is right here, right? I don't care what's in memory. Take the address of EBP minus 8, whatever it is, 12FF, whatever. Put that into EAX, right? And so why are we doing that? Because the next thing we need to push is the address of A. And while this may also be, the address of a.var1, it is the address of the start of this entire structure, right? So this is the start of the entire structure. So push this address because that's where the entire structure starts. So push that on there. That's the address of A, which we'll just say is, well, I don't want to make up numbers for this one. All right, so address of A goes there. And I'll call that EAX, I guess. Whatever's in EAX right now, that got pushed onto the stack. And then I'm going to do LEA of EBP minus hex 10 into ECX, right? So why am I putting hex minus hex 10? Right, so EBP minus 4, minus 8, minus C, minus hex 10, right? That's the start of B. That's the address of B, right? That's where the structure starts. So put that into ECX, push it onto the stack. Address of B onto the stack. ECX. And now I've got my 3 parameters to memcopy on the stack. Address of B, address of A, size of my struct. Now I'm ready to go ahead and call the function. Next instruction is call. All right, so now I'm going to call into memcopy. So I'm going to push the address of the next instruction, so 40102C. Right? 40102C. And then I'm going to go into memcopy, right? So this is kind of the end of this stack frame for main, the beginning of the stack frame for memcopy. I guess I'll take the actual values from this when I get through it. So, set a breakpoint there, run to there. All right, I got a bunch of stuff on my stack. Don't have my stack correctly positioned. All right, so I have not yet called the thing, so I don't have, that 401023 on my stack, but I do have 12FF58 and 12FF60 on my stack. So that's 12FF, wait, that's 5, 8, yeah. 5, 8. That's 12FF60. And this is 12FF60. And this is 12FF58. Right? So that's my stack immediately before, and you can see the 8 there as well. Right? And then you can see, what is that? That's B of R1. This is all in uninitialized data right here, actually. So you see above 8, I have B.var1, right? But actually, I never said anything to B.var1, so this right here is uninitialized, uninitialized, and then this is A.var1, our 0000FF, and then after that I have uninitialized. So that is the one thing you have to be careful about when, you know, looking at the stack and say, oh, I see 12FF. That must be, you know, some sort of stack pointer. Or it could be leftover uninitialized data left over from a previous stack frame that went down and then came back up, right? So, got some junk there. The only thing that matters is this right here. After the mem copy, I expect A.var1 to be copied to B.var1 right there. And also my uninitialized junk is going to get copied over that as well, but whatever. So that better be 00FF when I get done with this. All right, so call into the mem copy, step into it, got my 40102C on the stack. That's where our picture's at right now. And then I obviously didn't compile this with intermediate linking turned off again, so we got that intermediate jump, but I'm just going to live with it for now. All right, so here we are now at mem copy. First thing mem copy does, sets up its own stack frame. All right. So, bam, bam. It's saying the copy of the previous EBP, right? My EBP pointed here, which happened to be 12FF68. Go ahead and save that onto the stack, right? Push EBP. Well, so this is another, we'll put this in like another color or something. So, 12FF68. Save EBP. Right, first thing it does, then it sets its own EBP down to here. EBP, well, you know, the black EBP no longer matters, right? Real EBP right now is down here. All right, and then it pushes EDI, ESI. Well, ESI and EDI are callee save registers. We might think that's the case, or we could go confirm whether or not there's like a pop at the end. Well, let's see if there's a pop somewhere. Oh, there's a pop ESI, EDI. So that's probably the callee save registers. All right, so for what it's worth, ESI and EDI go onto the stack. ESI first, EDI first. EDI. Oh, by the way, if you didn't notice, we're reverse engineering now, right? We're reverse engineering mem copy. All right, so step over those two. I got whatever they are, stick them on the stack. All right, so now we have EBP plus C moving whatever's in memory there into ESI. All right, what do we know about EBP plus something? What sort of variables are those? No, Eric. Yes, those are parameters passed in from the function which is currently calling memcopy, right? So, EBP plus C, what is that? Well, EBP is plus here. Plus 4, right? We said plus 4 is always the saved return address. Plus 8 is always the first parameter. Plus C turns out to be the second parameter in this case. Okay, whatever. Nope, not that one. EBP plus C plus 8 plus 4 plus 10, right? 4, 8, 12, 16. Wait, I did actually not even get that there. All right, and what register does that go into? ESI. Okay. Said we're hunting for one of those rep instructions. We see something already going to ESI, which by convention is potentially a source register. A, the address of A was the source of memcopy. Whatever. This goes into ESI, equals that. ESI is now pointing at, well, so ESI actually gets the value stored in that memory, right? So we take whatever's inside of this address, EBP plus C, take this value out, stick it into ESI. So ESI equals 12FF60. All right, let's see if that's what we get for ESI register after we step through this. ESI 12FF60. Right? All right, next thing, EBP plus 10 goes into ECX. ECX is like that potential number of times we're going to do some operation. 8 comes out. ECX equals 8. ECX does indeed equal 8 after stepping over that. And then EBP plus 8, that's our first parameter, goes into EDI. Step over that, 12FF58 goes into EDI. So now we see EDI, which is potentially a destination register, points at the address of B. ESI, which is potentially a source register, points at the address of A. ECX, which is potentially a count register, has the value 8. Plot thickens. All right. ECX, which is 8, gets copied into EAX. So we're just kind of making a copy of it right now, right? So EAX now is also 8. Okay, ECX, which is still the count, also gets copied into EDX. So we now have another copy of it. So ECX, EDX, EAX, they're all 8 at this point. So potentially we're going to use those for something later. And now we're going to do adding ESI to EAX and put the result back into EAX, right? So ESI was that 12FF60 plus 8. Put the result into EAX, I should get 12FF68, right? In EAX after this. Step over, 12FF68. Now we have our first conditional kind of thing coming up here, right? We got to compare and a jump below or equal. All right, so compare ESI to EDI. Compare ESI to EDI. Compare ESI, EDI. All right, that's like sub ESI, EDI. That's like sub, well, that's like sub 12FF60 minus 12FF58. And then we're going to do this compare, and then we're going to do the jump below or equal. And I said before, you can kind of treat it like, when you have a compare, you can think there's like, you know, some sort of to be determined operator between the two things, right? So you can either go through and do the flags, right? So I can say right now the 0 flag is not going to be set, right? So at least that jump if equal side will not occur. And we have to worry about what is jump below. When does that occur, right? And we don't know right now. We don't know under what condition jump below occurs. And personally, I don't want to have to care. So I'm going to go back with this other way of thinking about it. There's some, you know, thing here, and it's a jump below. So I would say if this is below that, where below is sort of the unsigned notion of less than, right? So we have less than, in which case something is signed, and we have below if something is unsigned. What I'm looking for here is, well, it's a below or equal to, so is it less than or equal to that? So is that less than or equal to that? Is that less than or equal to that? No, it's not. Therefore, we expect this jump to fail. So if we are correct in our interpretation of, what it means to do this comparison, looking at one side to the other side with an eventual check for less than or equal, aka below or equal, then this jump below or equal should fail. We should fall through to the next instruction. Doing EDI, ESI. Yeah, I wrote that backwards. That's the problem. Totally got, I was like, I'm looking at the next instruction. I'm like, no, I know it's not going to, it's got to take the jump. I know, I've never seen that before. Write your instructions the right direction. Compare EDI to ESI. Try that again. EDI, ESI, right? And then we're just going to say, whatever this is, EDI is 12FF58. And, is that less than or equal to 12FF60? Yes, that is now, through the magic of writing the instruction correctly. We now will be taking this jump because 12FF58 is less than 12FF60. Yes, question?
So that actually means that the behavior of memcopy is going to depend on where the things you're copying are relative to each other in memory?
Potentially, yes, right? So she asked, does the behavior of memcopy depend on where the things are relative to each other, right? So we could have a case where we do memcopy address of B into address of A, right? So in that case, we would be copying from here to there, and then potentially this jump would go the opposite direction, right? But right now we're copying from here to there, and so it goes some other way. So this is what we're considering. This, we'll write out some pseudocode for what we've seen thus far when we get to the end of this. But this is our first unexplored path, is the fall through here. So we're going to take this jump, but something else is going to happen if we fall through. And we don't know what that is yet, but like she said, potentially it's got some completely different behavior if one thing is lower than the other thing versus one thing is higher than the other thing just in memory. So do that compare. We think we're going to take this jump and get rid of that. And we think this path where we fall through, that's some unexplored path right now. We're not going to take that, and so we'll leave that in the pseudocode for later. So I'm going to step into this jump instruction, and did it jump to, ED30? Yes, it did. We went to ED30 right there. So we jumped over this fall through path, which would have done a compare and potentially done a jump below. So now we have another compare. All right, what are we comparing against? ECX and hex 100. Well, what's our ECX right now? Anybody? It is 8. ECX and a constant hex 100. So is 8. And all right, and what's our next condition we want to check for? Jump below. So straight up, kind of less than, right? True or false? I'm getting a thumbs up from over there. All right. So 8 is below hex 100. So this is, again, something which we can think to ourselves. If that ECX, which is the size of my struct, is greater than hex 100, potentially memcopy is doing something completely different. All right? But all we know right now is we're less than hex 100. We're going to go wherever that's going to go. Jump if below, that's going to get taken. All right, so now we expect to go to ED57, right? Step, there we go, ED57, and we land immediately at a test instruction, which I hadn't successfully generated before, but what do we remember about the test instruction, Katie? What is it behind the scenes? So we said compare behind the scenes is a sub. Is a what? An add? Almost. You're off by one letter. It's an and, yes. So it's a bitwise and. So do we're going to do a test on EDI and 3. All right, what is EDI? Well, it's potentially our destination kind of thing. All right, so test EDI and 3. Test is an at. You got me saying it. No, I said it right. And. All right. Test is an and, right? A bitwise and. So you can think of it like we have EDI. Well, so which way do I want to think of it next? Okay, I got my upcoming jump not equal, right? So at least I can do this bitwise if I want. I can just say, is the result going to set the 0 flag or not? Or I can just, so this is a good example of where, I typically would do like a bitwise AND kind of thing, probably based on like 0 flag, because it doesn't make sense to put like greater than, less than signs in there because you're not doing like a subtract or anything like that. You're doing a bitwise AND. So you can't just say, is, 3 less than, whatever's in EDI. That doesn't actually work for this sort of thing. So I would typically make tests into the actual bitwise operations. Because they're typically, if you're doing tests, you're typically going to have some jump which is a 0 or something like that. Because the notion of greater than, less than, you wouldn't typically apply that to the result of some bitwise ANDing something together. So anyways, we're doing an AND on EDI, which is 12FF58. And we're ANDing that with, how do I want to write AND? There's so many nice symbols to choose from. I know, here goes that one. ANDing that with 3, right? So this is, this is again a hex thing. That's a hex thing. Let's take those nibbles and turn them into binary. Do 8 and 3. I take those, turn those into binary, and do the bitwise AND on those. 8 is 0, 1, 0, 0. 3 is 0, 0, 1, 1. All right, what's the result of that? 0, 0, 0, 0, right? There's never any 1 and a 1 together, right? So if those are 0 and all of these are zeros, right, those are all going to be 0 as well. So that's, anything ended with 0 is always going to be 0, right? So it doesn't matter what the rest of this is. We only cared about those bottom 2 bits potentially, right? And so, I saw some quizzical looks over there. Why do we even care about these 2 bits? Whatever, 2, 4, 6, 8. Put the zeros up here, but whatever. Result of this is 0, okay? We did an AND. We didn't store the results anywhere. We just set the flags based on the result. The result is 0. The 0 flag will be set, right? So 0 flag equals 1. ZF equals 1. Jump if not equal, aka jump if not 0, aka if this is not 0, we're going to take the jump. It is not 0 because it's 1, right? This is where the nots and knots get very confusing, right? Jump not 0 if this is not 0. Is the 0 flag 0 or is it 1, right? So just clearing my mind here for a second. Jump if not the 0 flag set. The 0 flag is set, therefore we are not taking the jump. Hold on a second. Okay, so we expect to not take the jump. So go ahead. Now you may ask your questions.
I'm wondering what SHR means.
SHR? Well, we're going to see here.
Right,
yep. Yeah. So that's the shift right, shift logical right that we saw yesterday. So move it over. So shift 2 bits. Well, that's going to be a divide by 4, right? 2 to the 2, 4. Anyways, we're not there yet. So, okay, now the question is, what's the deal with this instruction? Why is it doing this kind of thing? Well, under what cases would this go the opposite way? Under what cases would we not have something which results in 0? Right? So what would this have to be in order to have a non-zero value here? Anyone? Dave? Yep. Or 57 or any other things, right? So what he's saying is, these bits, at least one of these bits, either both of them or one of them, either or something, one of those bits needs to be 1. This bit or that bit needs to be 1 or both of them. And then we'll get a 1 here or 1 here or both of them 1s. In that case, we'll get a non-zero value. We will, 0 flag will not be set. And then, we'll take that jump. And so the question is, why are they doing that? Okay, I'll let you ask your question first. Yep, go ahead.
So is it checking to see if we're popping out of the middle of a word?
Well,
Because
that's
we've been
one way to
dealing
put
with
it.
4-byte words the whole time.
Right. So she asked, is it checking to see if we're copying out of the middle of a word? Well, not necessarily in copying out of, because EDI is potentially a destination, right? So maybe copying into the middle of something. So what she's getting at here is, the middle of a word, any address which has either of the lower two bits set to 1 is not a 4-byte aligned address, right? So all addresses which are 4-byte aligned must have zeros here, right? So what is an address ending with, so x50, x54, x58, x5c, x60, right? What do we know about all of these nibbles? Right? That's 0, 0, 0, 0, 0, 1, 0, 0. That's 1, 0, 0, 0. That should have been C right there. I don't know how I got a 6. Right, and then this is, again back to 0, 0, 0, 0, right? So for all addresses which are a multiple of 4, these bottom two bits are always going to be set to 0, right? So it's either got the 4-bit set or the, 8-bit set or the 16-bit set, but it can never have the 2-bit set. It can never have the 1-bit set, otherwise it's not a multiple of 4. So what it's checking is your destination aligned on a 4-bit boundary? Because this potentially means, maybe it'll be aligned, maybe it won't, because, are we trying to copy, maybe we could do a mem copy of 1 byte if we want, right? And in that case, this test would go some other direction potentially. And, well, strictly speaking, this test wouldn't be sufficient to determine that. But anyways, in some case, let's say we're not, well, let's just say in other cases, this test can fail if you have some destination address which is going to be, not 4-byte aligned, and therefore memcopy will go do something else. What that something else is, we don't know. We don't care right now because we don't think that jump's going to be taken. Because our result was 0. The 0 flag was set to 1. And therefore, the jump not 0 flag set to 1 is not going to be true. And therefore, we fall through to the next instruction, the shift right. So do that, and then, we don't think we're going to end up at ED74. We think we're going to fall through to the next instruction. All right, we did fall through to the next instruction. So now we're at a shift right, which we talked about yesterday. Shifting right is like a divide instruction, which divides by some power of 2, where the power of 2 is given as the number of bits that you're going by, right? So, just again, like we did yesterday, you had 0, 1, 0, 0, something like that. Right? And if I had that value, which, oh, hey, I do have that value, ECX is 8. How convenient. I didn't even mean to do that. This is my ECX. Right? My ECX, I'm going to shift it right by 2. Boop, boop, like that. 1, 0, 0, 0, 0, 0. And I said yesterday, with these logical shifts, they don't care. You get zeros in the top bits. 0, 0. All right. So that was 8. And that's 2, because I divided it by 2 to the 2, which is 4. 8 divided by 4 is 2. After this, ECX equals 2. All right. Do it. ECX equals 2. All right, now I have a proper AND where I'm going to store the result. And I'm going to AND EDX with 3, okay? Now back to what is EDX at this point? We did that copy before. We did like ECX copying it into EDX, copying it into EAX, right? So we had some copies of 8 laying around. Now we're going to take one of those copies and we're going to AND it with 3. Well, that's going to be a pointless thing, right? So 1, 0, 0 equals 8. And 0, 0, 1, 1 equals 3. Result. Right? So whatever this was checking for, again, maybe some sort of 4-byte alignedness or like not 4-byte alignedness, whatever. For whatever reason, it's ending that with the bottom 2 bits. And so we do that. EDX becomes 0. And that's fine because we're not using EDX right here, and we don't seem to be using it immediately sooner. All right, then we have a compare ECX to 8. Well, ECX was 8, but ECX is now 2 because we divided it by 4, right? So compare ECX something 8 to 8, right? And so this is 2 something to 8, right? And what's the condition going to be here? We have a jump below coming up next, right? The jump below is 2 less than 8, below 8. Yes, that is true. So we expect to take this jump below. But that means we're stymied because I see the rep move. I see it right there. I want to fall through. I don't want to take this jump. Something has gone horribly wrong. I could have gotten to that rep move. I'm so close. But at the last second, victory is snatched away. I take the jump below. I take some other weird jump, whatever. And then I end up in some array of moves. Okay. Well, if you look at those moves, what you'll find is, well, we're executing sort of 4 moves. Well, I'll say right now, we basically don't care what these are, but we do see, for instance, that these seem to be part of a larger chunk of moves, right? And we, for whatever reason, jumped into the middle towards the end, right? And so, intuitively, what we can think maybe is going to happen here is that my mem copy is now going to use individual move instructions to move var a.var1, move that to there, or potentially move it into a register and then move it there, right? So move this to a register, move the register to there. Move this to a register, move that there. Because we can't do memory to memory move, right? Except with that move string awesomeness. That's a different thing, right? That's move string. So anyways, let's see where our stack's at again. All right, do-de-do. Okay, there's our 8, so we know that's going to be right below B1, bvar1. So we're expecting, you know, this will maybe take, through some combination, it'll take a.var1 and move it to b.var1. And it'll take a.var2 and move it to b.var2. So, you know, if we wanted to calculate all this, we don't want to calculate that. So I'm just going to copy all that, open it up in another memory window. Okay, well, that kind of looks like that FF that we moved to a.var1, right? So we know this memory location right here is the a.var1 through whatever complexity that it decided to do. And, well, okay, so here's something I can say about this, right? We said before that most complicated form of the RM32 was base plus index times scale plus displacement, right? So index times scale. This ECX is being treated like the index. That ECX is 2, that's that 8 that got divided, right? And then, but we're multiplying it again back by 4 because maybe that scale is the size of our things that we're copying, right? So we have a 4-byte thing and then another 4-byte thing, and they're not really like 4-byte array. They're technically a struct, but the compiler doesn't care. As far as it's concerned, you've got, you know, 4 bytes arrays, and you're just trying to copy that 4 bytes to that 4 bytes, and that 4 bytes to that 4 bytes. So anyways, we kind of have a confirmation here that this is just going to do a sequence of move to register, move the register back to the other target thing. And it's just going to move it 4 bytes at a time, as opposed to doing it with the special rep move. So back to our stack. We're copying from here to a register, right? So what register? EAX. Right, got the 000FF. And then I expect I'm going to put that right there because that's my b.var1. Bam. Destroyed my b.var1 with the 00FF. And I can step through and I can do whatever else it's going to do, and I don't care because I wanted that rep move. And there we go. There was a leave instruction right there at the very end. It just flew by. Anyways, so now the question is, we were hunting for rep move. How do we get there? how can we change the logic? How can we change the inputs to memcopy in order to actually get to the move S? Right. So I'm going to bring back up like my instrumented disassembly, right? So again, you can go back through and you can look at this and you can see the description of why we think every given change is doing whatever. Yeah, so this is now, again, this is kind of getting to the essence of reverse engineering. We now got to a conditional point, and we took a jump that we didn't want to take. We took this jump below, which we didn't want to take. We need to start working ourselves backwards. I'm going to let you struggle with this for a second. Working backwards, we know that jump below happens because 2 is below 8. And then we know there was something that happened in order to make our 8 to a 2. And so, you know, how can we get backwards? And what input can we give to force it so that we do not take this jump below? All right, so without looking at your slides.
You had a bigger structure you're copying?
Yep. So if you had a bigger structure that you were copying, potentially you would not take this. How big does it have to be?
It would be 32 because you have to it has to be big, less than 8. We shifted 8 to the right. So
Yep. Yep. So he said it needs to be a 32-bit struct that we're copying instead, a 32-byte, sorry. All right, and why is that? Because we know that that size we had, we shifted it 2 to the right. That divided by 4. So x divided by 4 must not be less than 8. So it must be at least 8 so that, you know, if it's equal, this less than will not hold, right? So something x divided by 4 must be equal to 8, right? Solve for x. X is 32, right? 8 times 4, when divided, will give you this condition not holding. We will fall through, and we will hit the rep move. So let's try that. Let's increase the size of our struct, like so. Right? Let's see if this border condition holds. I just made my struct have now, instead of 4 bytes in the array, you can think of each of these as going to be like huge. This is going to be a 28-byte array. That's going to be a 28-byte array. But still, I would have 2 structs here. One's got a 28-byte array, and then it's got the var1, and one's got a 28-byte array, and it's got the var1, right? So just take this and like massively expand it. And now let's see if we actually can get to that rep move. And then let's see, you know, why potentially variables were getting messed with. Why was there that divide by 4? Well, think about it. All right, go to disassembly. Keep on trucking. Step into the memcopy, which is built with intermediate linking enabled. I'm going to get rid of that just to show you again. Under my linker, if I get rid of that incremental linking, I'll no longer have the call go to a jump. Step into, what? Cake is a lie. All right, whatever. Okay, so, sorry, that was the actual, that was the import address table. So that's fine. That's okay to go there. But, all right, anyways, so we're in memcopy. We're going to breeze on through here. La-di-da-di-da. Okay, well, after we had this 3 sequence, right, we had, you know, sort of EDI was the destination, ESI was the source, and ECX was the size. So now let's see, our size is hex 20. That's 32, right? So keep on popping around here. Got to that first jump. Did we take it? Yes, we did. Got to the second compare. Did we take it? Yes, we did. Got to this test, right? Now we're checking for alignment. Kind of no difference. It's going to be here. It's still going to be 4-byte aligned, right? And so now we fall through that jump. We shift our ECX hex 20 by 2, so divide it by 2. Divide it by 4. ECX is now 8. Right? We do this AND. This AND turns out to not have anything to do with anything we're doing. Right? That's for later. It's just setting up something for if it takes some other branch. And then we have compare ECX to 8, compare 8 to 8. Well, compare is a subtract instruction. Well, you can think of it like the less than, etc. So, is 8 below 8? No, it is not. And so we fall through to the rep move, right? And so now we can talk about the rep move in the context of that rep stos that we just saw a little while ago, right? Pretending that it would have worked in the small case, we would have seen that EDI was pointing here. So here, EDI, which I said can potentially be by convention, and this is the instruction which makes that convention. It's the destination. Oh, sorry, then that's not where it's pointing, is it? EDI is 12FF8, right? The destination, that's our source. EDI points here. ESI, double I, points there. Got a source, we got a destination, and we have an ECX, which was 8, right? We wanted to copy 8, but if we look again and pay attention to the D-word pointer thing that's tacked onto here, we're dealing with D-word pointers. That means we're copying 4 bytes at a time. So we don't want to execute this copying 4 bytes from the source, ESI, to the destination, EDI, right? And note we have ESI and EDI in angle brackets. So like we're taking this thing here from the source and putting it there, right? Right? So a single instance, we execute one instance of rep move S. It's going to take a D word from the source, D word from the destination, decrement ECX by 1, and increment EDI by 4, increment ESI by 4, right? So now these have stepped up so that I can get ready to do the next thing. And so ECX was equal to 2, right? But now we decremented that. We increment these. So now ESI is here and EDI is there, right? And we execute it one more time. So we take whatever's here, that's just some uninitialized junk, set it there, and then we decrement this. ECX is 0. We increment this. But then we check, is ECX equal to 0? Yes, it is. We're done with the instruction. Move on to the next instruction, which here is an unconditional jump. Yes, question.
What's the ES colon?
What's the what?
ES colon for EDI.
Oh, the ES before the EDI?
Yeah.
That's saying that technically it's using, so that's actually a segment register prefix. We don't talk about segments until the intermediate x86 class. And in practice, there's no difference on these segment registers because Windows sets all segment registers to the exact same thing. It's just basically this, back in the day, you would have like the ESI could potentially be, you know, one segment of memory, and I think it's technically the DS in front of this ESI, like it's not showing it here, but I believe it's technically using the data segment on the thing. And actually, if you look back to the rep stos, you would have saw that ES as well. So functionally, we don't care what that is. You'll learn about it in intermediate x86. So stay tuned. Anyways, so, you know, we have the big version of this now. We got to the rep move. You know, it's going to do it a bunch of times, 8 times specifically, 8 times 4, 32 bytes of copying. All right, and I can do those 1 byte at a time if I want, or 1 keyword at a time if I want. And then eventually I get down to this jump. Jump is, notice, it's this EDX, right? So I said that EDX didn't really matter to us before, but the EDX is used down here. So EDX was the size of, it was a copy, well, I guess it got turned into 0 actually, so never mind, right? Because we had our 4 byte aligned thing, and then it got ended, and then that turned into 0, right? So it gets turned into 0. I think what that would essentially be, I'm guessing here, I don't know for sure, this right here, if your EDI, if your size was not 4 byte aligned, right? So you did an end with these bottom 2 bits. If it's not something that's a multiple of 4, you would have got 1, or you would have got 2, or you would have got 3, right? It's like saying if you're trying to copy 33 bytes instead of 32 bytes, then you got one leftover byte that still needs to get handled, right? So your your rep move s did 4 bytes, 4 bytes, 4 bytes, right? So that can only copy in alignments of 4 for this, 4-byte version. You could use the 1-byte version. Potentially that's more inefficient, right, than just doing it 4 bytes at a time. So this jump is probably jumping you into an array, which would probably clean up that additional 1, 2, or 3 bytes if you had something that's non-4-byte aligned. But ours is 4-byte aligned, so it's 0. So take the jump, and we ended up here where it looks like it's just at teardown, right? So going to move that. Was there a question, Ariel?
Yeah, I'm not understanding why, given that this is a 4-byte move S,
Yep.
why when we had 8 bytes that we were trying to move, it dropped us into an individual 4-byte by 4-byte list of moves.
Right, this thing,
It
right?
seems like it could have just done this with fewer iterations.
This right here, right?
Yeah.
And so essentially that gets to optimization and what's more efficient, right? So in some cases, if you're, what you can imply from this example is, in some cases, for sizes less than 32, maybe it's faster to just use a couple of regular move instructions. If you're copying some larger size, larger than 32 or equal to or larger than 32 bytes, then maybe it's better to set everything up and go through this kind of spinning rep move s kind of thing. So the programmers of memcopies, we can now think through in our mind, they had some conditional check that they put into the memcopy that says, if the size of whatever you want to copy is less than 32, I'm just going to give you move instructions. Otherwise, I'm going to go ahead and use this rep move, probably for efficiency reasons, basically. So anyways, we do see that let's see, where am I? Get that. Right, so we're to teardown. We have this pop ESI EDI, right? We had those saved. Hold on a sec. What's that? EBP plus 8. E plus 8. Yeah, so there's an interesting point as well. Memcopy technically does return the destination that you copied the stuff into, right? So I never check it, I never use it, but memcopy does return, like, you asked me to copy from address of A to address of B. I succeeded, here's the address of B, right? So this last move instruction right there, EBP plus 8, right, address of B, it's going to return that. It's putting it in EAX, right, immediately before teardown. Putting that into EAX, popping ESI, popping EDI, right, got rid of them, and then, move ESP to EBP. Well, it didn't have any local variables that we saw. So sorry, the leave instruction is, as we said before, it's essentially move EBP to ESP, right, that direction, and then pop EBP, right? So move EBP to ESP, it's already there. Pop EBP, now we're back up to that. Return, now we got rid of that, right? And then now we're back into the caller. Looks like it's, that's a return. It's not like a return 12 or something like that, right? Therefore, we can imply that this is a cdecl function, memcopy. So now the caller is going to be responsible for cleaning up that address of A, address of B, and whatever. So, bam, 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 leave, return. There we go. Add 12 to ESP. Get rid of those stack parameters. And, then move your ace of base for success and tear down. Looks like it's using the nice convenient form, right? So got rid of that. And then just go ahead and move EBP to ESP. ESP would have been right there. Take it all the way back up. All that goes away. And then it's time to pop EBP and return. Nice. Any questions? I think we're at our break time. All right.